So welcome to lecture 28 of numerical analysis, MCS 471, an introductory course to numerical analysis. Today we will consider ordinary differential equations and in particular initial value problems. So this lecture is an introduction. We will define some terminology. It is also an overview. In the central part of this lecture, we will see a very basic method, Euler's method, and a modification, applying techniques of numerical differentiation and numerical integration. So in a way, it is an introduction, but also an overview of the methods that will be coming later on in this chapter of the course. So ordinary, by the way, is to distinguish from a partial differential equation. It's not so much the ordinary that has more the pejorative ring to it. No, there's nothing pejorative about ordinary differential equations. Also not really anything ordinary about this. In this course, it's mainly to distinguish the ordinary from the partial differential equations. So in the third part of this lecture, we will ask ourselves about how can we know that there is a solution? Is the solution unique? So that will be implied by Lipschitz continuity. And we do this before we can ask ourselves about the numerical conditioning about the problem. All right, then, let's look to what is now an ordinary differential equation, and in particular, what is the distinction between what we call an initial value problem and a boundary problem. Here we have our first example of an ordinary differential equation. So you see that we have equation that has a derivative in this. And what is important here, what I will kind of point out, is that we have a second order equation. So you see the 2 sitting in there. So this is a second order derivative. That's the first important thing to note about this. It has a derivative in there, and we look at the order. It's an equation, but unlike the very beginning of the course, we're not really looking for points, we're looking for functions. So here the independent variable is t. We're looking for an unknown function depending on t, which t traditionally denotes time. This is a textbook example. It's a second order of solution. So there are 2 parameters in this general solution. Call them A and B here, and we need extra conditions to fully specify this problem. So we can do this in 2 ways. With time, we will specify what happens in the beginning of time, the position and the velocity, 2 conditions. Or we can do this with a boundary value. We can say at the beginning of time, what is the initial position, and we can also impose a condition at the very end. Again, second order, to make this a fully specified problem, make this a well-defined problem, we need that the number of initial conditions needs to match the order of the differential equation. Here is an initial value problem where we impose 2 conditions. So the conditions are given by constants C1 and C2. So we say that C1 is the initial position, and I will underline here, circle the prime. So the initial velocity is c2. And with these two initial conditions, we can actually solve for A and B. It's a completely symbolic exercise. We give meaning to the A. The A is now the initial position, and the B is the initial velocity. So a textbook example has a very nice analytic solution. That's the ordinary differential equation seen as an initial value problem. So with the initial value problem, with these two constants, C1 and C2, there is a unique solution. If we see this as a boundary value problem, then we also have two constants. So we have two constants, we call them C1 and C2 again. So C1 is again the initial position, but C2 is the position, the value of u at pi over 2. Why pi over 2? Well, it's a periodic function. Pi over 2 because it means that then the answer is again b. So this is kind of a textbook backward example. We find very nice symbolic solutions. So this single equation can be interpreted as an initial value problem or a boundary value problem. So for the rest of the lecture and for the next coming 4 lectures, we will exclusively talk initial value. We then still have 3 lectures, one on boundary value problems. All right, let's look at the first example. So this is another textbook example. We look at a right-hand side, 1 plus y squared, and you will actually see that that is the derivative of the solution. So the first part of the exercise mainly asks you to verify. You can do this by hand, looking up what is the derivative, or you know this still, what is the derivative of y. Or you can use sympy. In this computational course, sympy could be very good exercise for sympy. Sympy might even be able to solve this problem. Also, there is a constant there. So this exercise is meant to show that there is a whole family of solutions. So depending on this constant here, and with the initial condition, you will, so the initial condition here, that will uniquely specify the solution. So actually the purpose of this calculus question is find the constant, so that there is a unique solution that satisfies this condition. All right then. Our first example was a second order. We will work in our numerical methods with first order equations. So there is a standard form. So the standard form is defined by 2 things. So there is the right-hand side function. The function is of 2 variables, but note that the y depends on x. So the function can be a simple Julia function, or it can also be a complicated program. The cost of our numerical methods will be expressed as the number of times we have to evaluate f. So that's the first part of the standard formulation. Give a function on the right-hand side, and then give an initial point, an x naught and a y naught. So the main point of numerical analysis is often that numerical analysis will always give some answer. It may not be an explicit solution like in the previous exercise, but it will always give an answer. And that's already one motivation to consider numerical methods. We will approximate the solution. So here what we are after is that we have a grid or a discretization of the space line or the timeline, and we have our H, the step line. So H was a character that appeared very frequently in the last chapter, was the step size. That character H will actually keep on continuing making its appearance. So H is the step size here. On this discretization here, we consider a fixed step size. Later on, we will see how to make variable step sizes. Two methods. We can apply methods from differentiation. So the first method is to use forward differences here. So we approximate the left-hand side. So if we look at the left-hand side and we apply methods from differentiation, that gives us one class of method. In the second class of method, we look at the right-hand side. So here you can see that we switch to a formal variable, t. So t stands for temporary variable. And the main variable here is the upper bound. So the 0, I should probably have generalized this into x naught. So that's still an improvement that I can make to the slides. All right, two classes of methods. Let us see what that gives us. So that will give us Euler's method. So we start with forward differences applied to the left-hand side. So we discretize the problem. So we start with a continuous problem, but then it becomes a discrete problem. So the continuous equation is then turned into a formula. So here is the formula. So it's still continuous. So we have at the right, we have x and h, and the function that we can evaluate. So we know y at x. So we can evaluate the right-hand side, and at the left is our new value. So we discretize everything, which means that the xn is at n step sizes away from our start position, and we find approximations for the function values at these steps. So you can see that this is again something that we did right before the midterm. We are approximating a function that is defined now by an equation. Euler's method is a very simple method, and it is defined by what I'm boxing in now. It is defined by this formula. It's an iterative method. You start at x naught, y naught, and you can evaluate the right-hand side to obtain y1. x1 is x naught plus h, so you can continue to compute x2 and y2. How good is this? Well, solving differential equations, so we are looking for a function, not any more isolated points, is a much harder problem than the problems we began with. We briefly also pointed this out with numerical integration. We no longer have a backward error. So what can we do then? Well, we can run our methods on equations where, and here's a very simple equation. So this is an equation where the right-hand side, so actually I'm underlining now what you actually define. The right-hand side function is just a function of y. And the initial value is 1. It's not the simplest possible. If the right-hand side would be a constant, then we all know that functions for which the derivatives are constants are linear functions. So, but linear functions are not so interesting. But in a way, already the simple right-hand side gives us a pretty wild function, gives us actually the exponential function. And Euler's method, what we apply is here we have h times the function evaluated. So the function is y, and we evaluate at x and y, yn. So running Euler's method one step is to add h times yn. Or we can factor this. And it's kind of nice, we can all the way turn this back to y naught. And actually we have an explicit formula for Euler's method. So Euler's method becomes quite simple. And you see we arrive at the limit definition of the exponential constant e. Something that you may have encountered in an earlier calculus class when the limits were introduced. So we will compute the limit now, but we do this with the Julia function. So here we are, the standard problem, the test equation, written here with the prime notation, y prime equals y. Let's do it. The Julia function is quite simple, so we actually don't need an entire function. But the nice thing about this, so here is the computation. So we start at step 0 and go to step n. The nice thing about this function is that it will give us a formatted table in the verbose mode. So we will run it verbosely when it has all the print statements, where we look at the errors. We know the exact exponential. So this is a quite nice function, a very simple setup. Here we see the h character. So we can, here for this test equation, we have one important character, our step size, but we can flip also to the number n. So n is important if we want to bound the amount of work that we are willing to do. So this is an iterative method, and we set a bound on the number of steps that we do. We will later see what happens to the accuracy by looking at the errors. So let's look at it. So this is a very simple test for 10 much. You see that the first error is 10 to the power minus 3. Well, the very first one is just the initial condition. So that's the sanity check. Do we start? And we do, error 0. And then we have 10 to the power minus 3 as the local error. So I'm using this output here to make the distinction between the local error, so the error of the first step, or the error that you make in one step, and the global error. So that's the error at the very end. And you see there is quite a gap. So after 10 steps, so we haven't actually done that much work, we only have one decimal place correct. So of our decimal expansion of E, 2.718, we actually only have the 2 correct. We haven't done that much work. Now, we can also visualize this. So this is good for a plot. You can see the plot here, where what we have is we can see the global error. So the global error is over here, the last dot, and you see there is a drift off. Even if we work on the very narrow interval 0, 1, this method is not so accurate. Well, we haven't done that much work. Let's do a little bit more work. All right, we run this for 10, 100, 1000, and we each time print the global error. So we don't run the method in verbose mode, we only print the error at the end. 1 million steps, 6 decimal places. So not so good. We need 1 million steps for 6 decimal places. Let's see if we can predict this. So first of all, why before we try to say something bad about Euler's method, you might argue, well, the test equation is exponential growth. What if you try exponential decay? That's the exercise. So there is a Jupyter notebook posted and also Julia programs posted for this experiment. So adjust the experiments, the code for the experiments, where now we know that we have exponential decay. So the question is run 10 steps. So apply Euler's method just as a sanity check with 10 steps. See, instead of plus h, you will do the minus. So the minus will come in. So it appears that you will step back, but you're not stepping back, you're forward, but your solution is exponentially decaying. All right. Compare this to the test equation. So if you have at the end of 10 steps, you have 1 over e, we can invert. So you can compare how accurate this is. So this is the absolute error. Step 2, in point of this exercise, compare the relative errors. See how Euler's method does on exponential growth and exponential decay. All right, that was not that good on our test equation. Can we justify this? Can we look at the error? Well, let's look at the Taylor series. So we expand the Taylor series. So the Taylor series at x naught actually corresponds at the left-hand side very, it is identical to the local error. So at the left, what you have at the left is what we will take as the approximation. So this, when you discretize this, this is y1. So this is y1. And at the right, you have y0. So that's here is our initial condition. So then the error here is actually the term that we neglect in the Taylor series. So it's not what I just underlined, but this big O. So that's the error on the first step, the local error. But we do n steps. So the fact that we had with 1 million function evaluations, that we had 6 decimal places is surprising, because 1 million is 10 to the power 6. So in general, the error is n times the local error. And here we have that n and h in our setting, we go up to 1, are inversely correlated. All right. All right. Let us see how we can improve the accuracy. So we derive a better method by actually taking one more term in the Taylor series, and by using some bootstrapping. So we have the second derivative that we now take, and we know that the second derivative is the derivative of derivative. So the bootstrapping that we apply is we apply forward the derivative equation, or actually the general equation. So I'm sorry. So we have the y prime. So we fill this in. X naught plus h is x1. All right, and this gives us a formula. This gives us the formula that will give us a better, a more accurate approximation. We went one step further in the Taylor series. And we will have derived the Taylor series, the modified Euler method. Now, if you just look at the shape, we have y equals y naught plus an average of two function evaluations. And this should somehow ring a bell. We did this with the trapezoidal rule. The modified Euler method, so I will skip a slide now to go to the next after slide, where we could have derived the Euler method all by, instead of doing the Taylor series and one step more in the derivative, we apply the trapezoidal rule to the right-hand side. So we take the antiderivative operator, so that resets, so the antiderivative is the antiderivative of the derivative operator. And at the right, we have, so you see the h over 2 coming in. And this is the formula for Euler's method. So that is the modified Euler method. So now I can go one step back. So form, if you stare at it for a little bit, I'm not going to stare at it. So I'm just, that here that's bothering us. So this is an our fixed point problem now. It seems like we have now turned, we don't really have an explicit method, because we, and if you do this, y1, if you do this for the first time, but in order to compute yn plus 2, you also need yn plus 1 at the right. Well, how can we solve this? We can do this with the predict correct. It's a simple method. It has a sufficiently good local error. So the local of this method, we can predict we use the predicted value in the formula for the modified method. Because of the Taylor, and actually now I should flip one slide back, I won't do this, because of the previous slide, and now I understand why the slides were in the order they are, so there is a logic to the slide. The local error, so the order of the local error, so of one step, is now h to the power 3. And we will see that this has some very nice, some very better accuracy. for the test function, so the test function is here back on top. For the test function, we have a more simpler implementation. So here the x is our xi. This is Euler, so y is Euler, and you see that the y is implemented here. Each time we then reassigning, we have y1 and we reassign the previous value to y0. So this is a bit of frugal implementation because we're only interested at the very end. All right, we run the function. So we have the predictor, the corrector, and you can see that the predictor the local error. So so here we do 10 steps. We see that also the predictor already has 2 decimal places. So you can also see again the local error and the global error. So Euler's method is kind of a good method to bootstrap us up to get a better value. Euler method is 10 to the power minus 4. The global error is 10 times larger. So here again we have the relationship between the interval 0, 10. We have the relationship between the local and the. All right, that was actually not that bad. 3 decimal places with 10. And we can do this for 100, for 1,000, 10,000, 100,000. 1 million is already quite, I mean, here it's not too much because the right-hand side is just a formula. But if this is running another program, you don't really want to do this. But in this setting, we have a better method. Same number of steps, 1 million steps, twice the accuracy of what we did. This is exponential growth again. So one can again say, well, the test equation is actually not so much. Let's do this with exponential decay. So the same exercise as the previous exercise. All right. So the test equation, not so much, not so interesting. Let's look to more general problems. So this is the last 10 minutes of this lecture. The problems are a lot harder. Sometimes the solution may not exist at all. So you can write down any right-hand side for which there is no explicit solution, but you may also have that the solution does not exist. Also, the existence, one may ask, is there a unique solution? So that the notion that we will be using will be Lipschitz continuity. And we will have to address this question before we can get to the numerical conditioning. So in this numerical analysis course, we always ask ourselves, what is the numerical conditioning? But here, because the problem is a lot harder, there might not be even a solution in general. So what is then Lipschitz continuity? So we will have to ask, is there a solution? And if there is a solution, then, well, is the solution is unique? So in order for that to that question, we need a more general notion of continuity. So we have a function of 2 variables, but note that the second variable y depends on x. So we have a relationship between the function values and the y. values. So what equation says here, so the equation that involves the constant, so we talked about exponential growth, and actually exponential growth, one has to be careful. So there needs to be a constant such that the difference in two function values f's of the right-hand side is bounded by the difference in the y value. And we look over a bounded domain, a rectangle S. So it's a more, so any function that is continuous will actually satisfy this, but one has to be a bit careful. So, so there is the continuity in y, and then there is also to look at some examples first. Here we have a function that where the set, the box, the rectangle, is for all x values between 0 and 1, and y can be any real number. Then what is the Lipschitz constant here? With a very simple equality, so x is actually positive, so the absolute value of x is kind of redundant, and we simplify this also in the inequality. So we have that here a straightforward example for a right-hand side function that is Lipschitz continuity on the set that we consider. Note that this is again a backward formulated example. It's so well because we have a restrict x. X is actually the upper bound on x, gives us our Lipschitz constant. So you can make something that is not Lipschitz continuous if the set imposes no restrictions. So one can immediately turn this into an example that is not Lipschitz continuity. So so one can also generalize this problem for separating y from x. So you have then a function, so generalization of the test equation where we have y, where we multiply with y with g of x, and h, we have an h function. Now it shows that the h actually doesn't really matter, but what is important is that g is bounded, doesn't have any asymptotes. All right, so if we know that the right-hand side is Lipschitz continuous on a set, so the set is actually quite important. So one can look at a very nice polynomial in two variables, but if one doesn't impose any restrictions, there cannot be a unique solution. So Lipschitz continuity implies the existence and the uniqueness of the solution. That's what this theorem here says. All right, here is another example. Now consider a nonlinear right-hand side. So right-hand sides that are nonlinear in y. Okay, let's try to compute the Lipschitz constant. And it turns out that the Lipschitz constant actually is now, we can actually frame this as we have an exact definition now for the Lipschitz constant is the maximum of x for any value of y. But know that y depend on x. So let's compute the value. So for which x values in the interval 0, 2 is there a unique solution? So we need to know the value for y, to the exact form for y. And this differential equation can be solved with sympy. So this is a symbolic solution of the differential equation. We have already seen how to define symbols. Now we can also define symbolic functions. So y is a function, and if we then compute the derivative, we can formulate the equation as a symbolic derivative. And with desolve, we obtain the symbolic solution. This is a first order equation, so it will contain some symbol, and we will use an initial value to substitute the constant in the solution. So this is the simple code, the simple sympy code. Here, so there is a Julia program that is posted. We see the output. So the print statements, we obtain the exact solution. All right, so with that exact solution, we can then compute the Lipschitz constant. So we can continue now with this example. So what we ended with was that the Lipschitz constant is the maximum over this interval. So the maximum of 2y. So how high can we take L? Well, note that we definitely cannot go beyond. So we look at x equals the interval 0, 2, but the exact solution has a pole. So the root of the denominator here is 1. So how close can we get to 1? Well, what's the Lipschitz constant you can't tolerate? Well, let's fix Lipschitz constant of 20. Then we need that y needs to be less than 10, and that imposes the bound on x. Okay, so that solves the problem for which there is a unique solution. So the value c is actually 9 over 10. So if we so we cannot do the entire interval 0, 2. We have to stop at 9 over 10. Here is a similar exercise, a little bit more general. So we now multiply the y square with x, redo the exercise. Sympy might also be very useful here to get to the general form. All right, last item. How can we think about the numerical conditioning? Given that there is a solution, if there is no solution, then the question of numerical conditioning doesn't make sense. Numerical conditioning, remember, I'm going to try to draw it very quickly. We had the conceptual picture with the space of the inputs, one oval at the left, one oval at the right. So we have 2 steps and 2 sets, and then we have in between the solution map. So we can look at our initial value problem as input. The input is actually the y naught. What happens, how sensitive is the solution changes in the y naught? Okay, and here you see we actually need Lipschitz continuity, because if we have the condition actually is involving the Lipschitz constant. So the L here is an important constant. And also we work with finite intervals. Here you see the drift off, and the changes at the right are the changes in the initial conditions. So y gives the capital Y. So note that I must backtrack a little bit. We have a unique solution for a given initial condition. But note that no matter what, we have families of solutions. So y and z are two members of the family, each with different initial conditions. So y has initial condition y at a, and z has initial conditions z at a. So then the difference in the solution actually grows exponentially. So we have actually a condition number. So the interval in the set, so the interval on x has to be bounded for this problem to make sense. So one can say that there is a condition number, but that condition number actually grows exponentially as we go farther away from the initial value. And that was also in the definition of the local error and the global error. So in the experiment with the interval 0, 1, we had the direct relationship between n and the step size. But of course, our interval was restricted to 0, 1. You cannot let your interval go unboundedly and then still expect to have a bounded global error. Here is another example. So we use this example in the family of Lipschitz continuous functions, where we have a very tame Lipschitz constant. So the condition number is this exponential function that we now can evaluate. So the exponential constant indicates that we do have a very well-conditioned problem, because we are bounded on the interval 0, 1. Very important. So we have a well-defined problem because of the Lipschitz continuity, and our numerical methods will also work well because we have a low condition number. All right, we are close to the end. Let's finish with one exercise. Let's look at the conditioning of our test equation. So we take a small change of our initial condition. So we have the y bar. We know what the solution is. Compute the upper bound on the error. So we still have the exact solution. So the first part, we do this with a numerical example. The second part of this exercise does this symbolically. All right, we made it to the end of this lecture. So what is important, there's a lot of it in this lecture, but we have seen the terminology. What is an initial value problem? What are the main methods based on numerical integration and differentiation? And we have to worry about uniqueness existence before we can address the conditioning.